Hi Math 1 students. I'm going to go over the first part of task 7.5. And this is about congruent triangles. Ultimately in this task we're going to use what we know about congruent triangles from the last couple sections to prove things about rectangles, squares, and rhombuses. So what we're going to start with is an amazing isosceles triangle. I gave you links for a couple of YouTube videos about isosceles triangles. If you've watched those already, that will help this go a lot easier. I have my filled out set of notes here already, so you can try to do the notes. You can copy my notes or copy some of my notes. You can decide through this discussion what you want to copy and what you don't. You can just pause the video when you need to take some notes, or you can just take all the notes first and just listen to the video for an explanation. So basically we're exploring isosceles triangles. Isosceles triangles have at least two sides are congruent. So usually we draw an isosceles triangle like this. If you had three sides congruent, it is an isosceles triangle. It's just a special type of isosceles triangle called an equilateral triangle. Equilateral meaning equal sides. Usually when we're drawing an isosceles triangle, we'll make two sides that are equal. Those are called the legs. We'll put a tick mark to show that they're equal. The top angle here is called the vertex. And we'll talk about the rest of that in a second. So Zach says that every isosceles triangle has a line of symmetry that passes through the vertex. The vertex is the angle that's in between the two congruent sides, so this vertex. And then it goes down, straight down, to the midpoint of this third side. Okay, so I just sketched this, so it's not a perfect drawing, but it will hit at the midpoint here. And Zach's friend says, yeah, that's a pretty big claim. How do we know that's true for every single isosceles triangle? Now, if we were in class together, we would try this with a whole bunch of different triangles. But since we can't, I'm just going to, I made a triangle with graph paper, and I'm going to use that to demonstrate some of the properties of isosceles triangles. I definitely need these two links to be the same, so what I did, I kind of worked backward. I figured out the midpoint that I wanted, and I counted off 5 spaces to the midpoint and another 5 spaces. And then I just counted up any number of spaces this way. It really didn't matter. I think I went 8 spaces up, and then I connected this with a ruler. So I know for sure that these two sides are congruent to each other. They would have to be just because of the Pythagorean theorem. And actually what we're going to do is we're going to fold the triangle to show this line, the crease basically. It's also called the altitude that connects the vertex to the midpoint of the opposite sides. And when I fold that, you can see that I have two exact smaller triangles on either side. Now that tells me a whole lot about an isosceles triangle. So it's impossible to check all triangles, but every isosceles triangle does have this line of symmetry that we're talking about. The line of symmetry by definition does cut the isosceles triangle into two congruent pieces, or it cuts it exactly in half. Okay, as long as all isosceles triangles would behave in the same way, then that's what's going to happen. And there's no reason to believe that any other isosceles triangle wouldn't behave in that same way, whether it's acute or obtuse or right. So what else does Zach need to know about the crease line? This line here where we're folding in half. That's also the line of symmetry, of course. So if we think about this line of symmetry, this crease line, as a line of reflection, then it tells us a lot of things. It must, this segment here must equal to that segment, so that tells us this bottom, the base or the bottom side gets cut in half. Okay. It also tells us the whole triangle formed on either side of the crease are also congruent because they land right on top of each other. They map right on top of each other. So basically we have two congruent sides. Okay. So the notes here would cover those two features that I just talked about when you were doing the reflection or folding on that line of symmetry. This triangle here, basically I had on a prior time that I did this lesson, I used a slightly different size triangle, but I have this triangle is completely marked up with all the things that kind of get covered on this page and the next page. So I just kind of taped it there so I would have it. But if you want to look at the printed notes or the PDF that I provided, you can zoom in and see all those parts and all those markings. So on page 41 now, I want to continue this on number 3. Sion thinks that Zach's crease line, this one where we're folding this in half, creates two congruent triangles inside the isosceles triangles, and we've just talked about that. Which criteria, angle, side, side, or side, side, could you use to support this claim? And so actually you can use any of those, and what we want to do is we want to mark the congruent parts on the triangle that represent these angles and sides that we would use to prove this congruence. So the first thing we know is that just because it's an isosceles triangle, we know that these two sides have to equal each other. So we have those two markings right off the bat with no argument. If we do a reflection here, and I'm just going to demonstrate it with my little triangle. If we do a reflection, then we know that this angle up top is going to equal that angle up top, and I've marked those with a single arc, and we name that angle BAD is congruent to the angle over here CAD. Remember that the middle letter of the angle name is the vertex of the angle. So angle BAD, this one, is congruent to angle CAD, this one. The other thing we can see from reflection is that these two angles at the bottom have to be the same. Those are actually called base angles. So that is angle B and angle C. And I only need a single letter to name these because angle B, there's no confusion about what angle B is. If I just said angle A up here, you don't know if I'm talking about the full angle A or this half or that half. So you have to be more specific. So angle B and angle C are equal to each other. They're congruent to each other. So I put two arcs on those. And actually we have enough markings here to be able to show we have congruent triangles. And we have, on both sides, we have angle, side, angle. Or you can go the other direction. Angle, side, angle are matching in two different triangles. So angle, side, angle is the reason why I know the left-hand triangle is congruent to the right-hand triangle. Remember when you're naming congruent triangles, this is called a triangle congruent statement. The corresponding angles need to be in corresponding order. So angle A is congruent to angle A. Those are the two up top. Angle B is congruent to angle C. That's those two. And angle D is congruent to angle D, which are these two inside right here. We don't have it marked, but those two would also be congruent. And you could convince yourself by using a folded triangle like that. In fact, it looks like those are also right angles in there, because we have that crease is perpendicular to that base. We'll talk about that later. Okay, here's another method. That was angle, side, angle. How about side, angle, side? Can we get that to work? Well, we still have these two sides marked as the same. Let's go ahead and keep these two angles marked as congruent. And if we do one more thing, if we look at this crease itself, the crease is part of the right-hand triangle, and the crease is also part of the left-hand triangle. It's called a shared side. The shared side is segment AD, and it's included in both triangles. So I say segment AD is congruent to itself. I like to mark it with an X. So we have these sides, this angle, and then the next side gives us congruent triangles by side, angle, side. Finally, if we look at this again, I'm going to use the sides of the isosceles triangle. I'm going to use the reflected the shared side down the middle. And then I'm going to use the sides here where we cut it in half. And I'm going to mark that with 2 tick marks on each side. So the reflection shows us that segment BD is going to be congruent to segment CD, and that gives us a third pair of sides. So we have congruent triangles by side, side, side theorem. All right, number 4. On this one is saying if 2 triangles created by folding an isosceles triangle in half are congruent, which they are, what does it imply about the base angles? So here's a labeled isosceles triangle. We have the vertex at the top. The 2 equal sides are called legs. The third side is called the base. And then the 2 angles down by the base are called the base angles. So when we fold this in half, then these 2 base angles are exactly equal to each other. They coincide. So therefore they're congruent. So in an isosceles triangle, the angles opposite congruent sides are also congruent. So if you look opposite this leg, you got this angle. Opposite this leg is this angle. Those 2 angles have to be congruent. Here's a shortcut way to write it. You would read it as if 2 sides are congruent, then 2 angles are congruent. Or you could say if opposite sides are congruent, then the opposite angles are congruent. All right, finally, if the 2 triangles created by folding an isosceles triangle in half are congruent, what does it imply about our crease line? So there's a couple things about the crease line. I want you to think about this. If I look at this crease line like this, it is shared in between these 2 triangles. What if I cut that in half? I don't have any scissors with me, or else I would. I've drawn it here. If I cut it in half, this crease line, this segment right here, is exactly the same segment on the left as it is on the right. So if I separated these 2 triangles, I could actually mark that with 2 congruent, with 2 tick marks to show that these 2 segments here are congruent. So the crease line is actually congruent to itself when you're thinking about 2 separate triangles. And drawing triangles, like separating the picture into 2 different pictures, 2 different triangles, sometimes is a nice way to look at the triangles, and it'll help you show that they're congruent. The technical property for a crease line being congruent to itself, or the shared side being congruent to itself, is it's called the reflexive property. All right, the other thing that we have here that we know about the crease line is, let's think about this. When we fold this triangle in half, these 2 bottom pieces are congruent. I've showed that with a triple tick mark. Okay, you can see that that crease line divides the base segment in half. So the crease line bisects the base. Okay, we have bisects the base. The other thing we have, that crease line, when we fold it onto itself, it creates these 2 right triangles that I talked about, these 2 right angles that I talked about earlier. This is basically 180 degrees. If you take 180 degrees and divide it by half, you get 90 degrees. So this also creates, the crease line also creates 2 right angles, which I've put little squares here to indicate that. So what do we have at the bottom? We have our crease line, and we have 2 segment halves and 2 right angles, which means we have a perpendicular bisector. The crease line is a perpendicular bisector of the base. All right, hopefully you understand all these notes. All of this, as a summary to those other 2 videos you watched earlier, will help you finish the quiz that is in Canvas, is worth 11 points. Don't worry if you don't get it all right. You don't have to get it all right. Just do your best and have a great day.